Hello students. In this video lecturing, we will continue with the fifth module, the next topic in the fifth module, that is hashing. Okay. Predicting the distribution of records. Last topic was the distribution of records, isn't it? Three types of distributions, that is uniform distribution, that is a distribution which is the best case, and then worst case, and one more was the random distribution, that is average case. In the that is in the worst case, it is like all the keys are pointing to the same address, and in the best case each address has one key assigned to it. Okay, so today we will start with predicting the distribution of records. Okay, it is nearly impossible to achieve a uniform distribution of records among the available addresses in a file. I told you uniform distribution means what? Each key is assigned to one address, that is a different address for different keys. That is called uniform distribution of records, but it is difficult. Okay, but we can predict how records are likely to be distributed, and based on that you can select the hashing algorithm. The Poisson distribution. Okay, in this we want to predict the number of collisions that are likely to occur in a file that can hold only one record at an address. That is predicting the collisions. We will derive a general formula to calculate the number of collisions, that is using the Poisson distribution. Okay, now what and all things we have to consider. What happens when that is you have a single address and you have a file of keys. Now this keys will hash to this single address. What is the probability that this particular address will be selected and this particular address will not be selected? We have to see. Then we will see for more number of addresses. Like that we are going to derive the formula. Okay, what are the things we have to consider when all of the keys in a file are hashed? What is the likelihood that none will hash to the given address? That is, no key will generate that particular address. Next we have to check exactly one key will hash to the address, that is to that particular single address one key will be hashed. Then we have to see more than two keys hashed to the address. I told you when there is a collision, those keys are called what? Synonyms. Okay, keep in mind synonyms. Okay, next we have to check for 3, 4 and so on. Keys will hash to the address. Then all the keys in the file will hash to the same given address. After considering all these cases, you can derive the formula for the probability. Okay, which of these outcomes would you expect to be fairly likely and which quite unlikely? See, there are n addresses in a file. Okay, when a single key is hashed, one key is hashed. Hashed means what? A key to a key, you are applying a hashing algorithm, and that particular algorithm will generate one value. Value means that is the address where the record is to be stored. Understood? That is called hashed. When a single key is hashed, there are two possible outcomes. Okay. What are the two possible outcomes with respect to the given address? That is, one is A, that is the address is not chosen, that is the hashed value is different from that address. Okay. B, the address is chosen, the key generates the same address there. Okay. In the first case, we say P of A, probability of the address not chosen. Then you have to calculate the probability of the address chosen. Okay. Now, probability of the address chosen, that is P of B, you can say it as small b is equal to 1 by n. N is the total number of addresses in a file there. Okay. And next is probability that it is not chosen. P of A. What P of A will give? 1 minus this one. Probability that it is chosen. Okay. 1 minus 1 by n. Yeah. Okay. 1 minus 1 by n. Okay. See, for example, one example is given here. If you have n, that n is equal to 10, that is you have n addresses, and B is equal to, that is the probability that a particular address is chosen is 1 by 10, that is equal to 0.1. B is equal to 0.1, and A, that is the address is not chosen. Out of 10, that particular address is not chosen, that probability that is equal to 1 minus 1 by 10, that is 0.9. Okay. Next is, suppose two keys are hashed. Now, just now we discussed when one key is hashed, isn't it? Now we'll consider when two keys are hashed, what will happen. Okay. Two applications of the hashing function are independent of one another. The probability that both will produce the given address is the product. That is probability. To check the probability, you have to consider the product of the two keys there. Okay. Now P of BB, that it is chosen, both the keys select the same address. The probability that both the keys, that is both keys, when it is hashed, it will select the same address, is that B into B, that is equal to 1 by n into 1 by n for n. In our example, for n is equal to 10, how much it is? 0.1 into 0.1, that is equal to 0.01. Okay. Next, second case, where the second key could hash to an address other than given address. See, you are hashing two keys, isn't it? And you have one address. Now you are going to check the probability that this particular address will be chosen by these two keys, isn't it? First we checked when both the keys choose the same address. Now we will see when one of the key, that is B, means it is choosing the that particular address, and the other one is pointing to some other address. In that case, it is B into A, that is probability that a key is chosen and probability that a key is not chosen. So it is 1 by n into 1 minus A by n, this one. Okay. Now for in our example, for n is equal to 10, what happens? B into A is equal to 0.1 into 0.9, that is equal to 0.09. Okay. Next, we are going to, in general, how you can say that. That is A raised to, that is, it is not chosen, A raised to R minus X. X is, that is, it will be chosen X times. You are considering an address will be chosen x times, and r is the number of records. Okay, in that case, a raised to r minus x, b raised to x. Okay, and the number of such ways is given by the formula. In general, one more formula is being given, and where r is the keys, when r keys are hashed, the probability that an address will be chosen x times and not chosen is r minus x. Now, so to this formula here, p of x is equal to c of 1 minus 1 by n raised to r minus x 1 by n into 1 by n. If x is equal to 0, that means we can compute the probability that a given address will have 0 records assigned to it. That is, you have an available space with an address, but no record is chosen by that particular address. Okay, is hashed to that particular address. To it by the hashing function using the formula, this one. If you substitute x is equal to 0, you will get the formula thus. Now, when only one record will be assigned to the given address, in that case substitute x with 1 there. Okay, now in general, what is the formula you can get? That is p of x. X is the number of times it is chosen. Okay, number of addresses it is chosen. Okay, p of x is equal to r divided by n raised to x e raised to minus of r by n divided by x factor. Okay, here n is nothing but the number of available addresses, r is the number of records to be stored, x is the number of records assigned to a given address, and p of x gives the probability that the given address will have x records assigned to its. If I say p of 1, that you are checking the probability that the given address will be assigned one record to it. Understood? Like that. So here x means applied to all n records. Next is to the actual general formula. You are going to substitute when x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3. What is the probability that no records are chosen? What is the probability? Initially we told you, told, right? That is in the Poisson distribution. We will see through. These are the questions to be answered. That is when x is equal to 0, x is equal to 1, x is equal to 2, and so on. You have to derive and see. Okay, when n is equal to 1000 and r is equal to 1000, that is n is nothing but the available address space is 1000, and you have the record number of records, that is 1000, then r by n is equal to 1. That is the probability that a given address will have no keys hashed to it is it, that is x is equal to 0. Substitute x is equal to 0 in the formula, you will get the value 0.368 there. Okay, now this is when x is equal to 0, same thing. Okay, next the probability that a given address will exactly choose 1, 2, 3 keys respectively hashed to it are, when one key is hashed, p of 1 is probability that one key is hashed to a particular address is 0.368 itself, same value you are getting. But when you have two keys, probability that two keys will be assigned to a particular address is 0.184, which is less than the previous one key. Probability that one key will be assigned, and three keys assigned to a particular address is 0.061. Substitute to this Poisson formula, you will get this value, that is 0.061. Okay, next is predicting the distribution of records. Whatever we discussed, we'll just conclude that when using a random distribution, We can use a number of mathematical tools to obtain conservative estimates of how our hashing function is likely to behave. Using the Poisson function, which we derived, the formula, this one, applied to hashing, we can conclude that. Using this formula, you can conclude that in general, if there are n addresses, that is available spaces, then the expected number of addresses with x records assigned to them is given by n into p of x. That is number of available addresses into probability of x number of keys assigned to that particular address. Okay. Next is predicting collisions for a full file. Say, for example, suppose you have a hashing function that you believe will distribute random records randomly, and you want to store 10,000 records, that is R is equal to 10,000 in 10,000 addresses, that is capital N is equal to 10,000. Okay. How many addresses do you expect to have no records assigned to them? How? R is equal to N is equal to 10,000. So R divided by N is equal to 1. Now the proportion of addresses with zero records is, that is the probability with zero records is P of 0 is equal to 0.3679, that is for 10 records. Earlier we have calculated this, isn't it? P of 0 is 0.39. Now for this 10,000 records, how much is it? Probability is P of 0 into 10,000, that is 0.3679 into 10,000. It is nothing but 3,679. Okay. How many addresses should have 1, 2, and 3 records assigned respectively? That is 10,000 into P of 1, the value which we have calculated earlier. The same values here we have taken 0.3679 into 10,000, that is 3,679. Next 10,000 into P of 2, 10,000 into P of 3. These are the values. Okay. Next, how much extra memory should be used? See, in reducing the collisions technique in the first video, one of the method was to increase the memory, isn't it? When you increase the memory, the number of collisions will decrease. So here we will see the see how we can reduce the collisions. What is the relationship between the collisions and the packing density? Okay. See, definition for packing density. Packing density refers to the ratio of the number of records to be stored, that is R. You want to store R number of records to the n number of available spaces, that is you have say you have 10 available spaces and you want to store 2 records. So R is to capital N is 10 there in the example. Okay. Now packing density gives a measure of the amount of space in a file that is used, that is the percentage of used space it will give, which one? The packing density. So how to calculate the packing density? It is nothing but R divided by N, that is number of records divided by the number of available spaces or available addresses, you can say. Okay. Here is an example. The packing density, this is the formula, number of records divided by number of spaces, that is nothing but R divided by N, number of records. R is number of records and N is number of available addresses or spaces. Okay. For example, consider R is 75 records, that is you have 75 records to be stored and you have 100 address space available. Okay, you want to store this 75 records in this 100 address space. So what is the packing density in that case? It is nothing but 75 divided by 100, which will give you 0.75, that is equal to 75%. That means out of that 100 available spaces, 75% is used. That is 75% of that particular available space is filled with the records. That's what it means. Okay. Predicting collisions for different packing densities. What is the number of collisions for different packing densities? How this collisions is dependent on the packing density. Okay. Poisson distribution allows us to predict the number of collisions that are likely to occur given a certain packing density. So we use the Poisson distribution to answer the following questions. Let's see what are the questions. First question is, how many addresses should have no records assigned to them? How many should have one record assigned? How many should have more than one record assigned? And how many record can be assigned to each home address? That is one record to each address, and which resulting in overflow. Then what is the percentage of records should be overflow records? Okay, so to this table here with the packing density percentage and synonyms percentage. When the packing density percentage is 10%, the synonyms percentage is 4.8. Synonyms is number of collisions or the keys which collide. Those are the synonyms. Okay, you have 4.8%. Okay, when you have the packing density is 40%, you have 17.6. For 70%, you have 28.1. For 90%, this much 34. 100%, that is 36.8, and so on. That means as the packing density increases, the number of synonyms or the number of collisions also increases in that. Okay. Next is collision resolution by progressive overflow. One of the technique to resolve the collision. How to resolve the collision? For the first technique we will be discussing is progressive overflow, or you can call it as linear probing. How this works is given in this second point here. We'll just read and then see to an example to understand this. Okay. If a key K1 hashes into the same address A1 as another key K2, then look for that is both K1 and K2 is hashed to the same address. What to do then? Look for the first available address A2, that is you look for the next available address, that address which is empty. Okay, following A1 and place, that is from A1 you have to start searching the addresses A2, A3, A4 which is free, and place K1 key in that particular address, for example A2. If the end of the address space is reached, that is you have total 100 available spaces and you have reached this 100th record, check 100th address to check if it is free, then wrap around where you have to move, that is move to the first location, that is called wrap around it. Okay, next, when searching for a key that is not in, that is you are going to search for a key in this progressive overflow, then if the address space is not full, then an empty address will be reached, right? When you go on searching, you will get an empty address and you have to stop there. Else, if it is address space is full, then search will come back to where it began, that is from where you started there, till there you have to go on searching. Okay, now we'll see how this progressive overflow works. See, you have a key York. Okay, this is the key, and using some, sorry, okay, this is the key, and using some algorithm, hashing algorithm, you have generated the address, that is 6. Okay, now 6 is called the home address of this key, then key, that is York. Okay, now you have to search for this home address here. Where is the home address? Here, this is the home address you got from the key York, but you already have one key here, that is Rosen. That means that particular address space is filled, and now you have a collision. Now, using linear probing or progressive overflow, what you have to do is you have to check for the next address and see if it is available. That is, next address is 7. Is it available? No, right? You have one key here, Jasper. So this is not available. Move to the next address, that is 8. Again, check whether this is free. No, you already have a key Morley. Again, move to the next one. This is called linear probing. Okay, you are going on checking linearly. Okay, next address 9. Yes, it is empty. So you can place this yacht here in this available space. Now you have to place your key, that is yacht here. Understood, right? In a linear probing or progressive overflow, how we are going to insert a key. Okay. Next, we will see another possibility of this. Okay. We'll understand what is wrapping around in the procedure I told you. If the record is full, you have to wrap around, isn't it? Now, so this is an example. Searching for an address beyond the end of the file. You are searching for the key, that is blue. Using hash function, you have generated the home address, that is 99. Okay. Now you are checking for blue in this home address, that is 99. It is yellow. It is not this key. So next, where you have to search. This is the end of the available space or the record address space meant for storing the records. Next, what you have to do? You have to wrap around, that is move to the first location, that is 0th location, and start searching from here for the key. If you are inserting the key and you got this as a home address and 99 is already full, then wrap around, go back and see to the 0th position. If nothing is there, you can fill blue here. Understood, right? What is a wrap around? Yeah. Next is a search length when using progressive overflow. Okay. Progressive overflow causes extra searches and thus extra disk accesses. See, if there are many collisions, then many records will be far from home, right? See, if I say you have 10 available address space and this if five of the keys are generating the address 1, then each of these keys will be stored far from the home address 1, isn't it? That's what it is. Okay. Now, definitions. Search length. What is search length? It refers to the number of accesses required to retrieve a record from secondary memory from the disk. The average search length is the average number of times you can expect to have to access the disk to retrieve a record. Here is the formula. Average search length is equal to total search length divided by total number of records. Okay, we'll see what is it, how to calculate the average search. Now, see to this table here, you have keys, 5 keys: Adams, Bates, Cole, Dean and Evans, and the home address is given. That is when you hash this key, you get this address. That is for Adams it is 0, Bates 1, Cole 1, Dean 2 and Evans 0. Now you have to calculate the number of accesses required, that is search length. How you get the search length? See, Adams 0, you have to place where you will place where is the Adams in this file? Actual addresses 0. Here at 0 itself you have Adams. So what is the number of access? It is 1. In one access you can retrieve this record. Okay, so it is 1. Number of access is 1 here. Next is Bates, second key, Bates. What is the home address? 1. You can place Bates directly in the first, it is there in first home address itself. So you need 1 access to retrieve Bates. Okay, number of access is 1. Next, Cole, which the home address is 1. Again, you here it is Bates, it is not Cole. Again, you have to search for the next address in progressive overflow. Now this is Cole. Okay, so how many 6 you need? 1, 2, 6. Okay, here. Next, D, the home address is 2. Already you have another key. So you have to search for the next one. So number of 6 is 1, 2. And for Evans, the this home address is 0 here. Okay, now if you have to fetch Evans, you have to, how many 6 are required? 1, 2, 3, 4, 5 6 are required. Okay, now how to calculate the search length? Number of accesses required to retrieve a record from secondary memory, that is the search length. Okay, now how to calculate the search length? It is the total search length divided by total number of records. See here in this table, what is the total search length? This one. You have to add all these divided by number of keys, that is 1, 2, 3, 4, 5. Total search length is 1 plus 1 plus 2 plus 2 plus 5. How much is it? It is 2.2. Average search length will come up to 2.2. Now see to this graph here. It shows the average search length and the packing density. As the packing density increases, the average search length also increases here. Thank you. Next topic we'll discuss in the next session.